The tumor microenvironment is an important factor influencing the development, advancement, and regulation of cancer. It not only shapes the biology of tumor cells, but also encompasses the surrounding environment that is essential for the tumor's survival, growth, proliferation, and metastasis. Hence, it is important to develop computational pathology tools to get a better understanding of the special characteristics of the tumor microenvironment. Using artificial intelligence for tissue phenotyping can act as a foundational element in the development of these computational pathology tools. Unfortunately, the datasets available for tissue phenotyping were too limited in terms of size and scope. Well, or this was the case, until PanNuke arrived. Welcome everyone to the Fantastic Datasets and Where to Find Them channel. In today's video, we will see in detail the PanNuke dataset. Now, you may be wondering, what exactly is PanNuke? PanNuke is an open semi-automatic generated dataset for nuclei instance segmentation and classification, with exhaustive nuclei levels across 19 different types of tissues. The dataset was created in 2019 by Yevgeny Gamper and Navitalemi Kovanani, researchers at the University of Warwick, Sweden in the United Kingdom. This dataset was presented for the first time in the article PanNuke, an open pan-cancer histology dataset for nuclei instance segmentation and classification. After 1 year, the authors of the dataset released a study called PanNuke Dataset, Extension, Insights, and Baselines, where they studied the performance of segmentation and classification models when applied to PanNuke and talk more in detail about the dataset. In this study, they also provide comprehensive statistics about the dataset and outline recommendations and research directions to address the limitations of existing deep learning tools when applied to real-world computational pathology applications. So, in this sense, the PanNuke dataset was created to advance research in medical image analysis, focusing on nuclear segmentation in pathology images. It aims to provide a benchmark for algorithms and models in the detection and classification of nuclei in diverse medical scenarios. We have seen so far what PanNuke is and what is its purpose, but let's look now about its content. The dataset consists of 455 visual fields, of which 312 are randomly sampled from more than 20,000 whole slide images at different magnifications from multiple data sources. In total, the dataset contains more than 216,000 labeled nuclei, each with an instance segmentation mask, making it the biggest dataset for nuclei instance segmentation. It contains 7,904 256 times 256 patches from a total of 19 different tissue types. The 19 types of tissues are breast, colon, bile duct, esophagus, uterus, lung, cervix, head and neck, skin, adrenal gland, kidney, stomach, prostate, testicles, liver, thyroid, pancreas, ovary, and bladder. The nuclei are classified into neoplastic, inflammatory, connective soft tissue, dead, and epithelial cells. The most interesting thing about the dataset is how was it created. The authors created it with an active learning approach, in which a learning algorithm can query the domain expert to obtain labels for those specific instances where the model is uncertain. Their approach consists of 3 parts, and each part consists of training the model on labeled data, model labeling the unlabeled data, and validation and annotation by the domain experts. The first part consisted of 3 different ensembles of segmentation models, detection models, and classification models, which were trained on public and internal datasets that the authors had available. Afterward, a label correction on the randomly sampled visual fields was applied by pathologists, based on the uncertainty. This process was done several times. In the table, we can observe the initial data for nuclei classification. As we can see, the authors added a non-nucleus category, since they were interested in detecting false positive nuclei detection or segmentation to preserve the natural distribution of variability in clinical routine visual fields. In the second part, a whole visual field nuclei classification model was developed, since the authors identified that a large number of nuclear labels depends on the surrounding tissue. This classification model uses a different network architecture than the classification model in Part 1 in order to overcome this situation. Here, the same three steps were performed in several iterations. First, train the model on all the data that was labeled in Part 1, but now with the new classification model. Then, label the unlabeled data, and at the end, select those unlabeled data for annotation by the domain experts. Once numerous reannotations and retraining rounds were performed, the final dataset was formed by combining the outputs of detection and refined segmentation models. This is achieved by identifying the common elements between the two and employing an improved classifier for the centroids of the instance segmentation masks. So, where can you get the dataset? You can download it from the official page of the University of Warwick by following the link that I am showing right now on screen. I will also leave the link in the description. Once you download the dataset, you can observe that it is divided into three folds. Fold 1 contains 2,657 images, Fold 2 contains 2,524 images, and Fold 3 contains 2,723 images. The files within each fold directory are images, NumPy file, that contains image patches of 256 times 256. We also have another NumPy file that is called masks, which is an array of 6-channel instance-wise masks, containing neoplastic cells, inflammatory, connective soft tissue cells, dead cells, epithelial, and background. And finally, we can find a types Python file that contains tissue type that a given path was extracted from. In this figure, we can observe an example of some patches of PanNuke and their ground truth annotation overlaid. As you can observe, the image contains the 19 tissues and the nuclei classifications that were discussed before. You must know that to use this dataset, you must follow the next usage rules. The dataset provided is only for research purposes and it is not allowed for commercial uses. The data is licensed under the following license. If someone intends to publish a research work that uses this dataset, the papers where the dataset was first used must be cited as following. Now that we got into the discussion part, I will tell you why is PanNuke the best dataset for nuclei segmentation and classification. As explained at the beginning of the video, the community has made significant efforts to generate open datasets for the development of algorithms focusing on nuclei segmentation and classification. Nevertheless, these datasets have general limitations in terms of size, may only offer sparse labeling of nuclei, or are only available for a small number of tissues. Additionally, publicly available datasets often exclude various artifacts present in whole-slide images, which are commonly found in clinical routines. Therefore, it is argued that currently available data in digital pathology provides only a partially realistic environment because it involves cherry-picked visual fields that are not truly a representation of the conditions where algorithms will be applied. This tendency introduces a risk of sampling bias, a phenomenon that has already been observed in a validation study of deep learning models applied to radiology images in real-world scenarios, where model performance dropped significantly. Consequently, when creating the PanNuke dataset, a random sampling of visual fields from a pool of 27,724 hematoxylin and eosin whole-slide images in 19 different tissues was performed, without excluding purposely visual fields. This strategy is intended to preserve the natural distribution of variability in visual fields and ensure a more comprehensive and realistic representation of the challenges faced in practical applications. Well, that will be everything for this video. Thank you very much for watching the video, and if you are more interested in the PanNuke dataset, I strongly recommend you to read the 2 papers created by Yevgeny Gamper and Navi Talemi-Kovanani. I will leave the link in the description. Also, if you like the video, do not forget to click the like button and subscribe to our channel to learn more about fantastic datasets and where to find them.